Hello students, today we shall take up chemical properties of haloalkanes. So to summarize, haloalkanes undergo three types of reactions, namely nucleophilic substitution reaction, elimination reaction, and lastly reaction with metals. Nucleophilic substitution reaction, as the name suggests, you can understand, the halogen will be replaced by another nucleophile. Now just to remind you, nucleophiles are negatively charged or electron-rich species. So the nucleophilic substitution reactions can be subdivided into two parts. SN1, full form is substitution nucleophilic unimolecular reaction. SN2 means substitution nucleophilic bimolecular reaction. We shall be discussing them in detail, but before that, let us summarize all the reactions which fall under this category. Now for haloarenes, nucleophilic substitution reactions and elimination reactions will not be there. Only reaction with metals will be common for haloalkanes as well as haloarenes. Now let's start with nucleophilic substitution reaction. So you can see it's written, when the halogen of haloalkane is replaced by another nucleophile, we are mentioning the symbol to be Nu minus because they are negatively charged or electron rich. The reaction is known as nucleophilic substitution reaction. So in general, we represent the haloalkane by the symbol Rx. When we are treating it with a nucleophile, then you can notice the X is getting replaced by the nucleophile. Such reactions are called nucleophilic substitution reaction. This is the major class of reaction in this chapter. A lot of reactions are falling under this category and very important for conversions. Okay. So I have written down all the reactions at one go. I've taken Rx as the symbol for haloalkane. The first reaction is with aqueous NaOH, where the nucleophile is OH minus. So you can understand, if you compare with this, since your Nu is OH minus, so X will be replaced by OH. That means it is a method to convert haloalkane to alcohol. But remember here, the NaOH taken should be aqueous, that means dissolved in water. Alright, and the byproduct will be NaX. So the first reaction is with NaOH or KOH. Remember, wherever we are using the term Na, that can be synonymous with K also. So this is the method for preparation of alcohol. So when we'll be doing the next chapter, alcohol, this reaction will be used as a method of preparation of alcohol. Second reaction is with NaOR dash, and the nucleophile, as you can see here, is OR dash minus. The negative charge is on O. So R dash is another alkyl group. Remember, R and R dash may be same or may be different. So here, since nucleophile is OR dash, so X will be replaced by OR dash, and the class of compound which we get here is called ether. If R and R dash they are same, then we call them symmetrical ether, and if they are different, then we call them unsymmetrical ether. This is also a name reaction which we shall be doing in the chapter alcohol, phenols and ether, which is the next chapter. This way of preparation of ether is called Williamson's ether synthesis. We'll talk about it in detail. Then next reaction is reaction with Nh3 ammonia. Now ammonia is a neutral nucleophile. It doesn't carry any negative charge, but it has a pair of electron which acts as a lone pair. So here the reaction will occur by loss of HX. One hydrogen from ammonia and X from haloalkane will be lost, and the class of compound which H will be getting is RNH2, known as primary amine. Why do you call it primary amine? Because you can see here the nitrogen is attached to one carbon and two hydrogens. So when nitrogen is attached to one carbon, the amine is called primary amine. We also have this chapter in our syllabus. This way of preparing amines is called Hofmann ammonolysis. Next reaction is with potassium cyanide. Potassium cyanide, the nucleophile is Cn- where the negative charge is on carbon. Okay, so the product which we get is RCN, called alkyl nitrile or alkyl cyanide. Now this is a very important reagent when we want to increase the number of carbon in the carbon chain. As you can see in Rx, suppose R is CH3, so CH3 and Cl, so it has only one carbon. But when you are treating it with KCN, you are getting CH3 CN, so we have increased one carbon. So quite often when we need to increase the number of carbon in a reaction, cyanide is a very useful tool, and such reactions are called step up reaction as the number of carbon increased. Now the next reaction you see, the nucleophile used here is AgCN, but the product you see here, the product is not RCN, rather a product is RNC. It is because silver cyanide is not an ionic compound, it is a covalent compound, and the nucleophile is Cn and the lone pair on nitrogen behaves as the nucleophilic site. So the product formed is RNC, called isocyanide, and not RCN. Such nucleophiles which can attack from two different sites. Cn is you can see when it is with potassium it has attacked through carbon, and when it is with silver it has attacked through nitrogen. Such nucleophiles are called ambident nucleophiles. This year also question came based on this in the board exam. A similar ambident ligand is NO2. You see when it is with KNO2, the product form is RONO, and when it is with silver, the product form is RNO2. Alright, so Cn and NO2, they are examples of ambident nucleophiles. There are many other examples, but for this chapter only these many will do. So here you can see I have also mentioned check reaction 4 and 5, 6 and 7, where you can see two different products using the similar nucleophile. There are certain nucleophiles which possess more than one attacking sites, usually two, leading to formation of different products. Such nucleophiles are called ambident nucleophiles. Examples: cyanide, NO2. There are many other. For the timing you can remember this. But let me tell you a hint for you to remember. You see whenever the nucleophile, the counterpart is silver, as here, you may notice the linkage has taken place through nitrogen. And when the counterpart is potassium, the linkage takes place through the other atom. So apart from nitrogen, what else I have here? We have carbon. So here the linkage took place through carbon. And here, apart from nitrogen, the counterpart is oxygen. So you can see here the linkage took place through oxygen. So that is just a method to remember. That is not a hard and fast rule, but just for remembering sake you can make use of this trick. Alright, the above reactions may occur in two different pathways. All these reactions which we have done, they may occur in two different routes. Okay, they follow two different routes, and that's how they are named as SN1 and SN2. I have already given you the full form of SN1 and SN2, but when you write SN1 and SN2, what you need to know, S you write, okay, N you write capital N as subscript, and don't write 1 as superscript. Alright, 1 should be together with S. That's how we write SN1. Exactly the same way we write SN2, like this. Don't write 2 here as a superscript. So let us try to understand what is SN1 and SN2 mechanism. SN1 reaction, you see, the type of reaction occur in two steps. In the first step, the carbon halogen bond breaks, leading to the formation of a carbocation, which will be having sp2 hybridization and a trigonal planar geometry. In the second step, the nucleophile attacks the carbocation, leading to the formation of the product. Now, since the carbocation is planar, the nucleophile may attack either from top or bottom or from right or left. Okay, depending on the orientation of the carbocation. If you are making a standing carbocation, then the attack may take place from right or left. If you are writing a sleeping carbocation, then the attack may take place from top or bottom. It means the same thing. And depending on that, the position of the incoming nucleophile will be same as that of the halogen, or it may be just opposite to that of halogen. Now, if your compound is optically active, then you will be getting a racemic mixture. Okay, the reaction is governed by stability of carbocation, and the reaction is favored in a polar solvent such as water. So how does the reaction occur? CH3Cl NaOH is the overall reaction I am writing first, giving you CH3OH and NaCl. As we mentioned that step 1 is formation of carbocation by the cleavage of CX bond. So you can see CCl bond is breaking. Cl being more electronegative will pull the electron towards itself. Now since bond breaking demands more energy, so the reaction is slow, and it leads to the formation of CH3 with a positive charge called carbocation, methyl carbocation here, and Cl minus is formed. Now this carbocation which is formed, it has a trigonal planar geometry. I have drawn a sleeping carbocation. So the incoming nucleophile, which is the OH minus forming from NaOH, may attack from top, leading to the formation of CH3OH, where OH is also forming on the same side as that of the halogen, or it may attack from the opposite end or the reverse side, and you can see I have put dotted lines here. That means the reaction is occurring from, and the product is forming where the OH is coming opposite to that of the halogen. Now if the starting material is optically active, then the product formed is also optically active. Now you have equal probability of forming a product with retention of configuration, that means Cl and OH are on the same side, and another product may form on the inversion of configuration, that means Cl and OH will be opposite with respect to each other. Now there is equal probability that retention and inversion may occur, and such reaction mixtures are called racemic mixture. Now this term is applicable only if the haloalkane is optically active. Okay, for optically inactive compounds such as this carry no meaning. So I have written here same side as that of the halogen means retention of configuration, or occupy the opposite position with respect to the outgoing halogen, that is called inversion of configuration. Now sir must have done with you chemical kinetics, or if he hasn't done yet, you will get to know. Since the reaction is occurring in two steps, you can see the first step is slow step and the second step is fast step. Now when a particular reaction occurs in multiple steps, the slowest step determines the order of the reaction. Okay, so here in the slowest step, how many species are involved? Only one. You can see the nucleophile has no role to play here. So the reaction depends on concentration of haloalkane only. So when we write the rate of the reaction by following the formula, rate is equal to K, which is the rate constant, into concentration. The square bracket means concentration, CH3Cl, and since the coefficient of CH3Cl out here was 1, so here the power is also 1. So whenever the power is 1, we call it unimolecular reaction. So sum of the powers of the concentration terms is 1, hence it is a first order reaction. Now how do I know whether the reaction will be first order or not? That depends on the nature of the haloalkane. Since the reaction is governed by stability of the carbocation, the answer lies in the stability of the carbocation. If your haloalkane is tertiary or allylic or benzylic, then exclusively they undergo SN1 mechanism. If it is primary or methyl, then the reaction is more likely to occur by SN2 mechanism, which we shall be discussing now. If it is secondary, then there is equal probability of SN1 and SN2 reaction, because you can see stability of secondary carbocation is coming intermediate between the primary and tertiary carbocations. So that's how we get different products, a mixture of products, in case the haloalkane is optically active. We have already discussed what is optical isomerism, so you know what we understand by the optical activity. This year questions came, 2021 questions were there from this portion.